Hi friends, welcome to Chemistry Travels. In this video, we won't be doing any complex chemistry concept as such, but certain basic things that we all should be knowing. Since we are chemistry students, students of chemistry, we should be knowing these basic things. One thing is the constant values. We have certain constants in chemistry. When we do the different concepts, we have certain constant values. And when we do entrance exams, mostly those constants would be given in the question paper itself. The values would be given somewhere maybe in the start of the paper or along with the question. They would provide the constant values that are needed. But it's always good for us to know some of them, the most common one or the most important constant values. The next thing that we will be looking through is the important conversions. We have certain conversions like from converting from one unit to another unit, we have certain conversions. So that also will have that, but it won't be given in the paper. You should know the conversion. So sometimes we might have to convert certain things. Everything in the question won't be in the same unit. So there will be cases when we have to convert certain units to another unit. So we should be knowing those conversions. And the last thing we'll be doing in this video is rounding off answers. That is when we have exams, we have this NTA type questions, numerical type answering questions. So where we have to fill in the digits. It comes even for JAM exam and GATE exam. We have such type of questions, NTA questions. So we have to give the answers in numbers. And that time they will ask round it off up to 2 decimal places, round it off up to the first integer, and things like that will be asked. And we should be knowing how to round off the answers because what we enter that answer and the answer key answer. Their original answer key is answer and our answer should be matching. So it's very important that we round off correctly or else we would go wrong and we would simply lose the mark even if we did the correct method, we followed the correct method, we solved everything right, but just because we rounded it off wrong, maybe we can lose marks. So let's move one by one, move on to the topics. So the first part is the constant values, the important constant values that all of us should be knowing about in chemistry. So the first thing is the most important that we all study from our basic classes, from our small classes. When we start studying chemistry as a separate topic, the first thing that we study or the first constant that we study is the Avogadro's number. So it is the number of units of a substance that can be in 1 mole of that substance. If you take 1 mole of a substance, it would have this Avogadro number of atoms, ions, or electrons. Okay, so that is Avogadro number and its value is 6.022 into 10 raised to 23. It is given by the symbol N and with the subscript A. Then we have the atomic mass unit. The atomic mass unit is the mass of 1/12 the mass of carbon 12 atom, C12 atom. We take an atom of C12, 1/12 its mass would be called the atomic mass unit and that has a value of 1.66 into 10 raised to minus 27 kilogram and it is represented by AMU. Okay. The next one is speed of light, which is given by the small letter c and it has a value of 3 into 10 raised to 8 meter per second. Then comes the charge of an electron. Chemistry is all about electrons, protons, neutrons, atoms, and concepts like that. And it's very essential that we know the charge of an electron, mass of an electron, and things like that. So charge of an electron is given by 1.602 into 10 raised to minus 19 coulombs. Coming to the Planck's constant, Planck came up with the Planck constant H. We have E equal to h nu. So where h is the Planck's constant and that is given by 6.626 into 10 raised to minus 34 joule second. It's essential that we know the units also, whether it's joule seconds or what each, because when we do problems, maybe some other terms would be in kilojoules or would be in hours or something. So we should know that when I'm doing substituting the value of Planck's constant, I should know that my Planck's constant is in joule seconds. So I should be converting other units also to joules and seconds and things like that. So know the units also. Planck's constant H is 6.626 into 10 raised to minus 34 joule second. This is one of the constants that we use very often. Then we have the mass. Mass of an electron, mass of a proton and mass of a neutron. given by M subscript E, M subscript P, and M subscript N. So mass of an electron is 9.1 into 10 raised to minus 31 kilograms. Mass of a proton is 1.67 into minus 27 kilogram, and even mass of the neutron is the same, 1.67 into 10 raised to minus 27 gram. Proton and neutron have the same mass. The next one is the Bohr's radius. Bohr's radius given by A naught, and we know that the Bohr's radius, for calculating the radius of an orbit, we use the formula radius is given by A naught into this n square by z. So that value 0.529. We have Bohr's radius. The radius is given by 0.529 n square by z, where z is the atomic number and n is the principal quantum number of that orbit or of that atom. Yeah, so we do that and we get the value in Armstrong. It's not in meters or it's not in SI unit, it's in Armstrong. Now the next one is Rydberg's constant. This R subscript H. This Rydberg's constant, where do we use this? When we talk about the line spectra of hydrogen, we have this nu bar is Rydberg's constant into 1 by Ni square minus 1 by Nf square. We have the formula in atomic structure chapter. We use this Rydberg's constant in the line spectrum of hydrogen, where we have this Balmer series, Paschen series, Brackett fund, all those series we have, there we use this Rydberg's constant and it has the value 1.097 into 10 raised to 7 meter inverse. It's not meter, it's meter inverse. And next is the Boltzmann constant, Kb. And this constant we find in the kinetic theory of gases. When we study the kinetic theory of gases, we have this Boltzmann constant and its value is 1.38 into 10 raised to minus 23 joule per Kelvin. And the next constant is Faraday's constant, F, which we use when we study about electrochemistry. We use the formula relating the Gibbs free energy with the E value, EMF of the cell, as delta G is minus NFE cell, where F is the Faraday constant and it has a value 96,500 coulomb per mole. And it's not exactly 96,500, it is 96,485. So that's rounded off to 96,500 for our easier calculations. Here. Then last, we have the universal gas constant R, a very commonly used constant. We have when we lot of places we use this gas constant, like ideal gas equation, where we have PV equal to nRT. So in a lot of the cases, in real gases equation also when it comes, so this R is a very useful constant and we have to remember their values, and it is very simple. R has, depending upon what my other terms are, whether my pressure is in atmosphere or bar or how I can represent, depending upon the other values, we can have different values for R. R is generally taken as 8.314 joule per Kelvin per mole. 8.314 joule Kelvin inverse mole inverse is a common value we used for universal gas constant R. But if you're converting it to calories instead of joules, if I'm using it in calories, the value would become 1.98 calories Kelvin inverse mole inverse. That can be taken approximately 2 for our calculation. To make our calculations easier, we can take it as 2 calories Kelvin inverse mole inverse can be the universal gas constant if you're using in calories. And now if I have my pressure in atmosphere, if my pressure is in atmosphere, then I have to use the constant value R to be 0.082. 0.082 liter atmosphere Kelvin inverse mole inverse. And if I have my pressure in bar, if my unit of my pressure is given in bar means, then I have to use the gas constant value to be 0.0831. Atmosphere was 0.082 and bar is 0.083 liter per Kelvin inverse mole inverse. So these are the constants that we have to know. These constant values that we should be knowing as students of chemistry. Understood? Next is certain SI prefixes that we should be knowing and their values. Very common ones we use, and we use them in every calculations also in our normal daily life problem solving questions when we do in chemistry. We use all those things. first two, three, we don't use that common. Tera, giga and all, we don't use common. But as we come down, all this milli, micro, nano, all those terms, we use it very commonly. So the first one will start with tera, the positive values. Tera or capital T, it has a value of 10 raised to 12. 10 raised to 12 corresponds to the prefix tera. 10 raised to 9 corresponds to the prefix giga. 10 raised to 6 corresponds to mega. And 10 raised to 3 is kilo. We all know that kilogram is 10 raised to, it's 1000 gram, like we know that, 1000. 10 raised to 3 is corresponds to kilo. And centi, like we have centimeter and things like that. So centi corresponds to 10 raised to minus 2. Milli is 10 raised to minus 3. Micro is 10 raised to minus 6. Nano is 10 raised to minus 9. Pico is 10 raised to minus 12 and femto is 10 raised to minus 15. These are the values for certain SI prefixes. Understood? Next is certain common conversions that we use. There are the simple conversions that we have been studying right from our smaller classes in our maths or where physics, maths, chemistry, everywhere, and certain little more higher level ones also, which we started using once we came to these higher classes. So length, volume, and mass. We all know the conversions. There's nothing to learn as such. We all know it, but I just wanted to put it up here so that we get the whole thing in one page. So length is kilometer. 1 kilometer is 1000 meter, and 1 meter is 100 centimeter, and 1 centimeter is 10 millimeter. We know that. Now coming to the volume part, 1 liter is 10 raised to minus 3 meter cube. When you convert liter to meter cube, 1 liter is 1000 ml. We know that. And if you're converting to meter cube, 1 liter is 10 raised to minus 3 meter cube. And 1 liter is also equal to 1 decimeter cube. 1 liter is 1 decimeter cube also. And 1 liter is also equal to 10 raised to 3 centimeter cube. 1 liter is 1 decimeter cube. It is equal to 10 raised to 3 centimeter cube, and it is equal to 10 raised to minus 3 meter cube. And 1 centimeter cube can be taken as 1 ml. 1 centimeter cube is 1 ml, and 1 liter is 10 raised to 3, 1000 centimeter cube, which means 1000 ml. That is the volume part. Coming to mass part, we have in kg, gram, and milligram. 1 kg is 1000 gram, and 1 gram is 1000 milligram. Now we have the temperature, and temperature can be represented either in Celsius, Kelvin, or Fahrenheit. The most commonly used ones are Celsius and Kelvin. We don't use Fahrenheit that much in calculations, but we'll just know it. So 0 degrees Celsius, it corresponds to 273.15 Kelvin, and for the easiness of calculation, we neglect that 0.15 decimal part and we just type 273 Kelvin. And to convert Kelvin to degree Celsius, we just have to take the degree Celsius, whatever temperature we are having in degrees Celsius. To that, if we are adding 273.15, I would get, or 273 if I'm adding, I would get my temperature in Kelvin. And next is Fahrenheit and Celsius conversion. So I'm converting Celsius to Fahrenheit. If I have a temperature in Celsius, I can convert it to Fahrenheit as the temperature in Fahrenheit is given by 9 by 5 into the Celsius temperature, the temperature in Celsius plus 32. 9 by 5 into the temperature in Celsius plus 32 degree. That would give rise to the temperature in Fahrenheit. Next, we have the energy term. Energy is mainly represented in joules or electron volts or in calories. So 1 joule, that joule term is kilogram meter square per second square. 1 joule is equivalent to 1 kilogram meter square per second square. And 1 joule, converting it to calories, we can see that 1 joule is 0.239 calories. 1 joule is 0.239 calories, and reverse of it, 1 calorie is 4.184 joules. 1 calorie is 4.184 joules. And the next famous conversion is electron volt to joule. 1 electron volt is 1.602 into 10 raised to minus 19 joules. 1 electron volt is 1.602 into 10 raised to minus 90 joules. That conversion we commonly use in solving problems. And last, we have the pressure conversions. Pressure can be in pascals, atmosphere, bar, then in torr, then millimeters of Hg, mm of Hg, mercury. So we have different conversions. First thing is Pascal. Pascal is Newton per meter square. 1 Pascal is 1 Newton per meter square, or in terms of kilogram, meter and second, I can write it as 1 kg per meter second square. 1 Pascal is 1 Newton per meter square, or 1 kg per meter second square. These are the terms related to Pascal. And Pascal and atmosphere, how are they related? One atmosphere is 101.325 kilopascal. It is kilopascal because I have a decimal point in between. It is 101.325 kilopascals. That is one atmosphere. Also, one atmosphere is 750 torr. In terms of torr, I can say that one atmosphere is 750 torr, or it is also equivalent to 750 of mercury, Hg. Understood? And next is bar in Pascal atmosphere. Bar is another unit that we use for pressure, and 1 bar is 10 raised to 5 Pascal, or that 1 bar is also equal to 0.987, approximately 1.987 atmosphere. 1 atmosphere is 1 bar is 0.987 atmosphere and 10 raised to 5 Pascal. So these are some of the important conversions that it's always good that we know them, so that we can solve problems easier, even if it's the conversions or the constants are not given in the paper. Next, we'll look at the rounding off of answers. Rounding off answers, like round off up to certain decimal places or up to a particular integer. We have to round up certain questions. So we'll use certain questions that has appeared in our JAM papers. I'll take 3 questions and explain how we can round off to the given decimal places that I've told in the question. And from JAM 2018 paper, I've taken 3 questions, and using those questions, we'll solve those questions also, and we'll learn how to round off also. So we'll learn 2 things. One, we'll be able to learn how we can do that particular question. Apart from that, we can understand how we can round off to the decimal places that they have given in the question. So here is the first question. Here they've told, consider the reaction, and the reaction is given: carbon monoxide, which is a gas, reacts with oxygen gas to give carbon dioxide gas. Okay. And the value of delta U for this reaction, internal energy, delta U value at 300 Kelvin, temperature is 300 Kelvin, is given to be, the delta U value is given to be minus 281 kilojoules per mole, and they want the enthalpy value, the value of delta H at the same temperature in kilojoules per mole. And they have asked us to round it off to the first decimal place, to 1 decimal place we have to round off, and the R value, the constant for R, is given to be 8.3. The whole value is 8.314, but they have asked us to use only 8.3. So when they have given the constant to be 8.3, use 8.3. Don't use 8.314 just because we know it. Look in the question, because that extra 314, those points can make huge difference in our answers. Because in such NTA type questions, in their answer key, they would have like the value from a particular range to particular range, from X to Y. If you that particular range, our answer should fall in that range that they have given. Even if we are a decimal point extra or a decimal point less from their range, we wouldn't get the mark. So we should be very careful. Use R as 8.3 itself because they've given it. Now, how do we solve this question? We'll just look at this, how to solve this question. So this is from thermodynamics, and we know that from thermodynamics we have the equation. So we have one of the equations in thermodynamics as delta H is given by delta U plus P delta V. We can have it like this: delta H is delta U plus P delta V. This is the equation we have. Or instead of P delta V, from ideal gas equation, I can write that to be delta nRT. So this can be written to be equal to delta U plus delta nRT. Okay. Now I just have to substitute the values. For substituting the values, the first thing that we should be knowing is delta n value. What is delta n? It's not given. So from the equation, we have to find delta n value. So just look at the equation first. So we look at the equation here. Delta n would be the difference in number of moles. So it is the number of moles of product minus number of moles of reactant. So that would be Number of moles of product is 1 mole minus number of moles of reactant is 1 mole of carbon monoxide plus half moles of oxygen. So this is 1 minus 1 plus 1 by 2, that's 3 by 2. 1 minus 3 by 2 is minus 1 by 2. Okay. Now I got delta N also. Delta U is given in the question in kilojoules. Delta N I got. T temperature is 300 Kelvin. R is given as 8.3. Remember, R is given in joules. But my delta U is in kilojoules and I have to calculate delta H also in kilojoules. So let me convert my R value to kilojoules and then substitute. So 8.3 joules can be taken as 0.0083 kilojoules per Kelvin per mole. So using all that in the calculation, here I can substitute as my delta H would be equal to minus 281.8 plus that delta N is minus 1 by 2 which I got into R it is 0.0083 into 300. So when I do all this, my value would come out to be minus 283.045. This is the value I get. Minus 283.045 is the value that I get. And they've asked us to round it off to the first decimal place. Now, how do we do that? For doing that, so what we have to do is just look here. Here, after the decimal point, I have 0. So I have to take the first decimal place. So 0 I take. And now look at the next digit. So right next to that, I have 4. 4 is the number. If I need one decimal place, first decimal place, the number next to that first decimal place, they're telling us to round off to the first decimal place. So just look at the number next to the first decimal place. So next to the first decimal place in my answer, I'm having 4. Now this value that I have, the number next to the first decimal place, if it is 5 or greater than 5, then my first decimal place value, whatever I'm having, it would be increased by 1. If I'm having 0, that would change to 1. If the number next to the first decimal place, if that value of that number is 5 or greater than 5, then my first decimal place value should be increased by 1. Or if else it will remain the same. Now here I have next to the first decimal place I am having value 4. 4 is less than 5. It's not equal to 5 or greater than 5. It's less than 5 only. So I can leave my first decimal place number as such. I don't have to increase the value. It would remain as minus 283.0. So I would get the answer to be minus 283.0. This would be the answer rounded off to first decimal place. And in the answer key for this question, they had given the value to be minus 282.0 to minus 286.0. This was the range that they gave. Minus 282.0 to minus 286.0 was the range in the answer key, and we got an answer in between that, which is minus 283.0. Clear? So the next question is, to assuming the ideal gas behavior, the density of oxygen gas at 300 Kelvin and 1 atmosphere is dash. And it should be rounded off to 2 decimal places. And R value, because my pressure is in atmosphere, R value is taken in atmosphere and it is 0.082 liter atmosphere, mole inverse, Kelvin inverse. And molar mass of oxygen is given to be 32. Now, so here we have to use the ideal gas equation, and firstly they've asked us to calculate the density. The ideal gas equation is given by, we have the ideal gas equation to be PV equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. Where is density in this? We don't have density. But what is the equation of density? Equation of density, we know that density rho is given by mass by volume. Density rho can be given by mass by volume, and we know that the number of moles is given by mass by molar mass. Any given mass by molar mass would give rise to the number of moles. So I have number of moles in my equation. So instead of number of moles, I can substitute mass by molar mass there. And I can arrive at density equation. From PV equal to nRT, I can derive an equation for density. Now coming back to our equation. So here, instead of number of moles, I'm substituting mass by molar mass into RT is there as such. So this implies that then I can take my V to the other side. Then it implies that P equal to MRT by V and the other things. M is already there. This M by V that I got here, when I took the V to the other side, to the right side, that M by V that I got would become my density. So I can say that my P equal to rho RT by M. Right? So I can say that my pressure into molar mass divided by R into T would become equal to the density. This is the equation I got. So on substituting values, pressure is 1 atmosphere into molar mass of oxygen is 32 and R was given as 0.082 into temperature is given as 300 Kelvin and the value comes out to be 1.3008 approximately. This much gram per liter is my value coming. Now I have to round it off to 2 decimal places. So in this question, they have asked us to round it off to 2 decimal places. So 2 decimal places means what I do is, let us look, 2 decimal places. So the first 2 places, round off, 2 decimal places I took. And then the next digit I have to look. So up to how many decimal places we have to round off, up to how many places we're given in the question. Up to how many places we have to round off, take that many places. So earlier question it was 1 decimal place. So we took the digit next to the first place. Now here in this question it is to be rounded off to 2 decimal places. So take the first 2 decimal places, that is 3 and 0 are the first 2 decimal places. Then look at the next number. The number next to the 2 decimal places, that is a 0. The value is 0. If that value is greater than or equal to 5, then we have to add 1 to my this earlier value, the 2 decimal places. That is, if the third digit, because I have to round off to 2 decimal places, I take those 2 decimal places, I keep it as such. I look at my third decimal place, and if that third decimal place value was 5 or greater than 5, means if it was 5 or greater than 5, then this 2 decimal 30 would become 31. But here it is 0, which is less than 5. So I can leave this number as such. The 30 can remain as 30 itself. So my answer would be, for this would be 1.30. 1.30 is the answer that we get. And in the answer key, the range was 1.29 to 1.31. This was the range given in the answer key, and we got our answer in between this range as 1.30. Understood? So here we have the last question for this video, and I have a personal attachment to this question because when I wrote my JAM exam in 2018, I had this question. I got the answer right, but because I did not round it off correctly, in the question it was told to round to the nearest integer, but I rounded off my answer to the nearest decimal point, and because of that I lost 2 marks for this question, even though my answer was right, because their answer key and my answer is not matching, because they asked to round off to the nearest integer and I rounded off to the nearest decimal place. So you guys don't make that mistake when you do this question or such questions. So be careful, read the question clearly. And the question says that the electron of a hydrogen atom is in its nth Bohr orbit having de Broglie wavelength of 13.4 Armstrong, and the value of n is dash, and we have to round it off to the nearest integer. The earlier 2 questions were for rounding off to the decimal place, and here it is to the integer, and they've given the radius of the Bohr's orbit to be 0.53 n square. Pi value is given to be 3.14. So it's 3.14, and in the question value, it's value, when u is missing. So okay, so now according to de Broglie's hypothesis, when we studied the de Broglie's hypothesis, we would have studied this, the orbit is there like that, and my electron is moving means the wavelength it is taking this path means we would have studied something like this. And we've studied in de Broglie's hypothesis that but the circumference of my orbit is an integral multiple of the wavelength. This is something that we all would have studied when we studied the de Broglie's hypothesis in atomic structure. So now since my orbit is circular in shape, the circumference can be taken as 2 pi r, and 2 pi r is an integral multiple of the wavelength. So 2 pi r equal to n lambda. So from here I can say this is implies my r equal to n lambda by 2 pi. Okay, this is one equation that I get, equation number 1 for radius. From the hypothesis de Broglie's concept, I can get one equation. The second equation is already given in the question as the radius is given to be 0.53 n square. This 0.53 Bohr radius, that constants, when we studied the table for constant, we studied the values 0.529 Armstrong. So that is rounded off and taken as 0.53. So radius is given by 0.53 n square. Now this is equation 2. Now I have two equations for radius. Since the left hand side LHS are the same, I can equate the equation. So I can say that, so here I can say that n lambda by 2 pi from the first equation, that is equal to 0.53 n square from the second equation. Now I can cancel off one n from here and one n from here, and then I can write that as implies my n can be written as lambda by 2 pi into 0.53. Now implies, substitute the values, lambda is given as 13.4, it is in Armstrong, by 2 into pi is given as 3.14 into this is given as 0.53, that is also in Armstrong. So my wavelength can be in Armstrong. Okay, Armstrong. But if my wavelength was in some other meter or something means or my centimeter or something means I would have to convert it, because why? Because one is in my 0.53, that constant value is in Armstrongs. For that we should be knowing that 0.53 is in Armstrong. It's not given in the question, but we should be knowing that 0.53, that constant value is in Armstrong, and my wavelength is also in Armstrong. So I need not do any conversions in this. So when I do all this, my value would come out to be 4.02, and they've told us to round up to the nearest integer, and because it's an integer asked, we don't have to convert the fractions, the value, the decimal parts. The correct answer is 4. 4 is the right answer. We get the answer upon calculation to be 4.02 approximately, and that should be rounded off to the nearest integer value. So I don't consider the decimal part, it is 4. And in the answers key, the answer was 4 to 4. Their range was 4 to 4, which means 4 is the only answer. You put any other value, you wouldn't get marked. So this was how we should be solving this question and how we should be rounding it off to the nearest integer. So that's it for today. Hope you guys enjoyed this. Thank you so much.